ready? Okay, then I'm delighted to announce our next speaker for our last speaker for today. It's Alexander Gennadievich Kuznetsov, who's going to talk about categorical resolution of singularities. Alexander Gennadievich, the stage is yours.
Thank you very much. It's a great pleasure and honor to speak here. So actually, when I was a student in the university, of course, I've heard the name of Sabir, and I mean, for me, he was like the author of a huge volume, like something that you see in on the shelf of your parents, like Pushkin, Tolstoy, Dostoevsky, so 3 big names. And much later, I became more familiar with him, and it was not as intimidating as it seemed to me before. So it's really a great pleasure. Thank you very much for the invitation to speak here. Yeah. Okay. Good. Okay. One more thing that I need to say before starting is to say that, of course, I am kind of exterior person for this conference. So my main topic is kind of different. So I'm mostly working in the categorical part of algebraic geometry. So I will speak about categorical resolutions of singularities. And since this is quite far away from most of the participants, I will be slightly kind of vague and hand-wavy. So instead of giving explicit and precise definitions, which I think will be useless in this situation, I will try to draw a big picture of the subject. So, yes. Okay, then I am happy. Thank you very much. Okay, so yeah, so I will talk about the categorical point of view on singularities, on resolutions of singularities, and more generally on algebraic geometry. So what's that? What is a categorical point of view? So essentially, this point of view builds up on a very general observation, which is of slightly philosophical nature. So it may be true or not quite true, depending on the situation you are working with. But in a very general form, it tells you that if you want to study the geometry of some space, then for many purposes you don't need to have the space itself. For many purposes of your study, it's enough to have an appropriate category of shapes on this space. So it may be, I mean, in the topological setting, it may be the category of shapes of abelian groups on a topological space. Or in algebraic geometry, it may be the category of coherent or quasi-coherent shapes on an algebraic variety. And I will be mostly in the setup of algebraic geometry. So for many purposes, you don't need to know what is a point of your space, what is a curve on your space, and other things of that sort. But what is sufficient for many purposes is to know what is the category of what is the appropriate category of shapes on your space. I will try to illustrate this. So in some sense, the goal of my talk is to illustrate this principle in some particular examples. So the categorical point of view means that, okay, maybe let me tell you one thing right away. So when you, for instance, study some algebraic variety, then there are many questions about this variety which can be formulated in the sense of describing various moduli spaces of sheaves, right? So, for instance, if you want to think about, say, lines on a given projective variety, then this is the question about the Hilbert scheme of a particular kind. And this is a modular space of sheaves on your variety. And when you have the category, the category of coherent sheaves, then you can talk about the modular space without knowing what is a space itself. Yeah. So you can consider various modular spaces of objects in your category without thinking about actual geometry. Okay, so the categorical point of view is that we replace space. So let me put it in quotes because it may have different meanings in different situations by appropriate category of sheaves. That means that we just have a category which we consider as a category of sheaves on a space. We just study it from the perspective, we just think of this category as being the category of sheaves. Formally speaking, this is just a category that has properties similar to properties of a category of sheaves. So we replace space by a category of sheaves. Okay, and in many cases, yeah, so in the situation when you have an actual space, this is just one actual category of sheaves that you can consider. And of course, if you want such a replacement to be working well, then you need to be able, I mean, in the situation when your category comes from an actual space, you need to be able to maybe reconstruct the space from the category or almost reconstruct the space from the category. And there are various situations in algebraic geometry when you can really do it. So, for instance, there is a famous theorem of Gabriel that tells you that if X is an algebraic variety, then you can reconstruct X from the category of quasi-coherent sheaves on it. So in some situations, this is really well defined procedure, right? So if you know this category with all the structures that it have, then you can reconstruct the space, and therefore if you have a similar category, then you can really think of it as a category of say, quasi-coherent sheaves on an algebraic variety, even if there is no algebraic variety of that sort. For instance, you know, when your variety is affine, then the category of quasi-coherent sheaves is just the same as the category of modules of the corresponding algebra of functions. And this algebra of functions on an affine variety, this is a commutative, finitely generated commutative algebra, right? So then you can definitely, this category is quite similar to the category of modules of some non-commutative algebra, which is not very far from a commutative algebra. And so you can, in this way, you can talk about non-commutative geometry, just working with category of modules over non-commutative rings, thinking of them in the way as if it is the category of quasi-coherent sheaves on an algebraic variety, and trying to apply the same technique and the same approach. And this really works in some cases and helps understanding and helps proving results. So for instance, one typical example is that, so what is an affine plane? An affine plane is just equivalent to considering the ring of polynomials in two variables, right? And two variables in the polynomial ring, they satisfy the relation that their commutator is 0, right? You can replace this relation by saying that the commutator of two variables is 1. And this will be the Weil algebra, and you can study it thinking of it as the algebra of functions on a non-commutative affine plane. And this really works. There are lots of results of this sort. Okay, so one type of categories which one can associate to algebraic varieties are just categories of quasi-coherent sheaves. Sometimes it is more convenient to consider the smaller subcategories of coherent sheaves inside. This is a very close approach. For many purposes, this category is more convenient. For some purposes, this category is more convenient, and there is not there is no big difference between these two. But from some points of view, it's better to replace these categories with something quite different, which is the derived category of coherent sheaves. So, and that will be my point of view. So instead of, and I will try to explain why. So we will consider so I will write d of x, which is the bounded derived category of coherent sheaves on x. Sometimes it's also convenient to consider a slightly different category, which is called the category of perfect complexes. This is the subcategory in the derived category. And the difference is that so in the first category, the objects are just bounded complexes of coherent sheaves. And every coherent sheaf is just a co-kernel of a morphism between two locally free sheaves. And in this category, we consider those complexes which have finite locally free resolution. When the variety X is smooth, there is no difference between these categories. So these two categories agree if X is smooth, but they are quite different when X is singular. And since my topic is precisely about singular varieties and their resolutions, for me this difference between these two categories will be crucial. So this is why I'm mentioning it. If you are happy to work with smooth categories, then you don't need to distinguish between these two. So one category is a subcategory in the other. So dperf is a subcategory in d of x. So here you consider those objects of this category which satisfy a certain finiteness property. So those that have a finite locally free resolution. Yes, this is a full subcategory. Yeah. Okay, so what about this reconstruction theorem? So here there is also a result which is slightly different, and this is a famous theorem of Bondal and Orlov. And it tells you that sometimes you can indeed reconstruct X from its derived category, but not always. So it tells you that if the canonical class of X is ample, or minus canonical class of X is ample, in either of these two cases, you can reconstruct the variety from X. There is. I mean, there is a properness assumption, and if you have an ample class on a proper variety, then it is projective.
And in the first theorem?
No. In the first theorem, no. From D of X. In their theorem, actually, they consider smooth varieties, so it doesn't matter which category to consider. They are just the same. There are versions of this result for singular varieties, but you have to be more accurate because for a divisor class to be ample, you need it to be Cartier or Q Cartier, so you still need to impose some constraints. But let me state it in this form from D of X. Yeah, actually one more thing is that for a sufficiently wide class of varieties, you can reconstruct one of these categories from the other. So for proper varieties of perfect fields, you can do it. So from this point of view, reconstruction from D of X or from D perf of X, it doesn't matter. So yeah, but you see, there is an additional assumption about positivity or negativity of the canonical class. And of course, one can ask if this is a necessary assumption or this is just a feature of the proof of this theorem. And it actually a feature of the situation, not of the proof. There are, in fact, examples where different algebraic varieties have the same derived category. So the first example was constructed by Shigeru Mukai quite a long time ago. He proved that if A is an abelian variety, then you can take the derived category of A and you can take the derived category of the dual abelian variety. And these two categories will be equivalent. So this is the dual. And the variety itself, in many cases, is not isomorphic to its dual variety. If you take a general abelian variety of a sufficiently high dimension, it is not isomorphic to its dual, but the derived categories are equivalent. So that's one example. And another example of a similar sort, if S is a K3 surface, this is a very important class of algebraic varieties, then there are many examples of equivalence of D of S with D of S prime of D of S equivalent to D of S prime for S prime, another K3 surface which is not isomorphic to S. So yes, absolutely. That's precisely the point. So, yes. In both these examples, the varieties are smooth. Yeah.
So even if the conditions of one of these two theorems hold, can we also say that if we have an equivalence between two categories, it is then this equivalence is induced by isomorphism between two varieties? Or
Yes. Yeah. Almost. So. Talking about whether equivalences are induced by isomorphisms is the same as describing the group of auto-equivalences of a given variety. And for any variety, the group of autoequivalences may be quite big. And under this precisely the same two assumptions, you can describe it. So let me add it to the theorem. So the group of autoequivalences of d of x is isomorphic to the following group. So there are three pieces in this group. So there is a factor isomorphic to z, which corresponds to shifts of grading inside the derived category. And there is also the Picard group of x, which acts by twists with line bundles. And one more factor, and I hope I wrote the sign correctly, is the group of automorphisms of x. So not every autoequivalence comes from this factor, but there are two other pieces, but they are well understood. Yeah. Again, if these assumptions are not satisfied, then a priori you may have many more non-trivial autoequivalences. So what I want to say is that from the point of view of derived categories, the situation is more complicated, and you can think that it is less nice than from the point of view of these abelian categories of coherent or quasi-coherent shifts. But in some sense, the picture becomes more rich and more interesting, because you really have examples of different varieties which have the same derived category, and therefore they have many common properties. So maybe it's better to think of this as different faces of the same okay, I don't know how to say it, but you know, that's situation is more complicated, but it's really more interesting. So so you see that from the derived category, you not there are situations when you cannot reconstruct your variety, but still it the different varieties that correspond to the same category, they are still very close to each other. In this situation, one variety is an abelian variety and the other variety is an abelian variety. In this situation, you have two K3 surfaces. And you can prove that many invariants of derived equivalent varieties are indeed the same. So this does not create any problem in thinking in this way. On the other hand, there are some very interesting examples of categories which look like derived categories of varieties, but which are not equivalent to derived categories of actual varieties. So one example of a category of this that has a very similar properties, but which is not equivalent to anything like that, there is a very simple and very intriguing example. So let X be just a hypersurface of degree 3 in a, say, complex projective space of dimension 5. So this is a 4-dimensional cubic hypersurface. Let it be smooth cubic hypersurface. Then you can consider its derived category, and you can consider a subcategory in this category. So let me call it C sub X. This will be the subcategory of all objects which have some cohomology vanishing. So here we just take OX of 1 is the restriction of the corresponding line bundle from the projective space. And here we twist our object by O of 1 and O of minus 1 respectively. So we just want 3 different twists of our object to have no cohomology. And this is a very nice subcategory in D of X. And the point is that this category looks very much like the derived category of a K3 surface. So this category has the same invariance as D of S for S K3 surface. But if X is so very general, so I will explain what does it mean in a moment, then this category C sub X is not equivalent to D of S for any S. So very general means the following. So we are talking about cubic hypersurfaces in P5, and to specify such a hypersurface, we just need to specify a polynomial of degree 3 in 6 variables, right? A homogeneous polynomial of degree 3 in 6 variables. So there is a big vector space that parameterizes all these polynomials. Of course, we need this polynomial only up to rescaling, so there is a big projective space that parameterizes all such hypersurfaces. Also, it makes sense to take the quotient by the action of GL6, right? Because if you change the basis in your space, then the variety doesn't change. So there is still a big moduli space that parameterizes such cubic hypersurfaces. And very general means being in a complement to a countably many divisors in this moduli space. So it's not the usual generality assumption in algebraic geometry, but it's something slightly more complicated. You don't remove just finite number of hypersurfaces, but countably many hypersurfaces. But if you are working over some big field like complex numbers, if you remove countably many hypersurfaces, you are still left with lots of points, right? So there are, I mean, for almost every cubic hypersurface, you will not have such an equivalence. And thinking of this category as a category of shapes on a non-commutative K3 surface is quite helpful, because there are different phenomena for the cubic for this 4-dimensional cubic hypersurface that suggest that there is some K3 surface associated to it. For instance, as I was trying to explain before, if you consider some particular moduli spaces of shapes on a cubic fourfold, you will be surprised to see that they have a hyperkähler structure, something which is very rare in algebraic geometry. And the reason for this hyperkähler structure appearing is precisely that there is this subcategory which you should think of as a non-commutative K3 surface. I don't understand. Can you repeat?
So if it's not generic, then such K3 surface does exist.
Mm-hmm. Yeah. I should have said that indeed there are many examples when this category is equivalent to, you can find countably many hypersurfaces in this modular space when indeed this category is equivalent to the derived category of K3 surface.
Those K3 surfaces are algebraic.
Yes. Yeah, so the picture is the following. So if you want to classify algebraic K3 surfaces, then you need to fix some polarization on this K3 surface. So there are modular spaces of K3 surfaces with a polarization of a given degree. So for each positive even integer, there is a modular space which is 19-dimensional. So you have countably many 19-dimensional modular spaces. But the modular space of cubic fourfolds is 20-dimensional. So there is this 20-dimensional modular space, and inside there are countably many divisors that correspond not to all, but to some modular spaces of. Yes, this is different. I mean, it looks similarly, but it is different. Yeah.
What do you mean by classify?
When did I say that? At what point I said classify? I don't remember already. Classify. No, I'm not going to. Some people did. Okay. Yeah, I mean, you can define a certain modular space that will, whose points will correspond to K3 surfaces. Yeah, I mean, this is a very classical subject due to Shafarevich and Petetsky-Shapira. I mean, it comes from that. Yeah. I mean, there is Torelli theorem for K3 surfaces, which is responsible for that. Okay, so what I want to say is that there are many examples of very nice categories which look like non-commutative algebraic varieties, and it is profitable to consider them, to take them into consideration when you discuss even classical problems of algebraic geometry. Okay, so I think I need to give the definition, at least, of a categorical resolution, otherwise there will be no singularity in my talk, right? So, yeah, but let me point out one more thing before I will do that. So, as I said, I'm going to replace algebraic varieties. So maybe let me write varieties by triangulated categories. So derived category of coherent shapes is an example of a triangulated category, and this category Cx that I consider here is also an example of a triangulated category. So the one part of a categorical point of view is that in your study you replace varieties by triangulated categories. So, and I think of these triangulated categories as D of x. And of course, to do geometry, we usually don't need just one variety. We need also morphisms between varieties, so maps. So what do we replace maps with? And what we replace them with are functors between the corresponding triangulated categories. So actually, it's better to consider pairs of functors, pairs of adjoint functors. So whenever you have some morphism like that from x to y, in this situation you have the push forward, the derived push forward functor from d of x to d of y, and there is also derived pullback functor from the perfect derived category of y to the perfect derived category of x. Derived pullback. So we have these inclusions, and these two functors are adjoint, which means that if you want to consider morphisms from a pullback of one sheaf to another sheaf, this is the same as to consider morphisms from your original sheaf to the push forward of that sheaf. So it's like a junction between two operators, and this is how you should think of that. So yeah, and this is the point of view of this is the categorical point of view. So if instead of two varieties you have two triangulated categories, still to give a map between the corresponding non-commutative varieties is the same as to give an adjoint pair of functors like that between two categories here and the perfect versions of the same two categories downstairs. Okay. So from this point of view, it's very easy to define what is a categorical resolution of singularities. To do this, we just need to remember what does the usual resolution of singularities mean. So if X is a singular algebraic variety, then there is a very classical and the very important and one of the most cited theorems in algebraic geometry. This is a theorem by Hironaka that tells you that there is a proper birational morphism map pi from a smooth algebraic variety X tilde. So, his theorem is actually more precise. You can obtain such X tilde by a certain algorithm. You should apply the standard procedure of the blow-up to various subvarieties inside the singular locus of X. And in this way, you modify only the singular part of X, and then you finally obtain a smooth variety. And the example, I mean, like the simplest example to keep in mind is to think of the situation when X is just a cone over some smooth algebraic variety, right? Then it has a singular point, the vertex of the cone, and then to obtain such a resolution, you just need to blow up this point, and then instead of a cone, you will get, so if this is an affine cone, then you will have an A1 bundle over the corresponding smooth variety, or in the projective situation, you will have a P1 bundle over the same base. So this is a very standard and very useful procedure in algebraic geometry. So it allows to reduce many questions about singular varieties to much more simple questions about smooth varieties. This is really very useful. Okay, and then, so how can we define a categorical version of a resolution of singularities? So assume that we still have a singular variety, X, but now we want X tilde to become non-commutative. So we want to replace it by a category. And since we want to have a map, therefore, from that point of view, we need to specify two functors which should satisfy this adjunction property. But it makes sense to ask for something more. So let me give you a formal definition, at least one. So a categorical resolution of X is a smooth and proper. So I will assume that X is proper, smooth and proper triangulated category D. Maybe let me write D tilde, and functors. So one will be called pi upper star, and it will be from d perf of x to d tilde. So maybe let me write pi upper star here. Another one will go from d tilde to d of x to the bounded derived category of coherent sheaves. And there are two assumptions. So the first assumption is that pi upper star is left adjoint to pi lower star. So this is just the standard assumption that we have for this categorical point of view. And the second assumption is more is different. So the second assumption is that the composition of these two functors, so if you go from this perfect category to d tilde and then to d of x, we want it to be isomorphic to the canonical embedding of this subcategory into d of x. And I will just write that this is the identity functor. So this is a slight abuse of notation, but I think it's okay. So these are two properties that we assume. So the first, as I said, is a standard property from the categorical point of view. So let me give some comments about the second property. So the first one is that why do we require this at all? So as I said, in some sense, the very essence of a resolution of singularities is to replace a singular space, a singular variety, by a smooth variety, which is easier to deal with. So, and from the point of view of categories of sheaves, why do we need this? We need to be able to consider sheaves on X as sheaves on something smooth. And for this, we need the pullback functor that allows you to carry our sheaves on X to sheaves on X tilde to be fully faithful, right? This is like Grisha asked whether a functor is whether the space of morphisms are the same or not. So we need this functor to be fully faithful, and actually this condition is equivalent to full faithfulness of this functor. So let me write it. This is equivalent to pi upper star being fully faithful. So in some sense, this property is precisely the property we need from a resolution of singularities. This is what makes it work. On the other hand, there is a remark that I have to mention, is that if x tilde is a usual resolution, is a Hironaka resolution, let me write it like that, then in general it does not give you a categorical resolution. It is not necessarily a categorical resolution. So this second property does not always hold. So you can consider this, actually it holds only when the singularities of x are not very bad. So precisely you need the singularities of x to be rational for this to be true. For instance, if you start with a cone over some algebraic variety, then the condition on this smooth variety, on the base of the cone, you need to impose to have this property for the Hironaka resolution, is that the structure sheaf of this variety doesn't have higher cohomology. So this is a very restrictive assumption. for instance, if you start with a cone over a plane curve, over a smooth plane curve, then even if the curve has degree 3 or higher, then this property doesn't hold. So that's like a bad news, but the good news is that still categorical resolutions of singularities do exist. So this is a theorem that we proved long ago with Valera Lunz. It tells you that for any say separated scheme of finite type over a field of characteristic 0. So this means in a very large generality scheme X, there is a categorical resolution. So in some sense, the point of this theorem is that the Hironaka resolution may be not good enough from a categorical point of view, but you can improve it in such a way that it behaves very nicely from a categorical point of view. So these categorical resolutions do exist, and sometimes, I mean, they exist in situations when they even exist in situations when it's even hard to say what is a usual resolution of singularities. So maybe let me give you an example which is very simple but kind of striking, is that let us take the simplest possible singular scheme. So what is the simplest possible singular scheme? So this is just the spec of k of x mod x squared, right? So this is not what you usually consider when you do differential geometry, but for algebraic geometry, this is very useful and very standard scheme to consider. So this is, I mean, sometimes people think of this as an abstract tangent vector, right? So what is a resolution of singularities of this thing? And you can check that you can construct, actually you can construct many categorical resolutions of singularities here, but one example is the following. So you can take the following 5-dimensional non-commutative algebra. It will be the algebra of paths, the path algebra of a quiver with 2 vertices, 2 arrows, and one relation that the composition of two arrows in one order is 0. So you can take the representations of this quiver, and you can take derived category of representations of this quiver, and you can check that this category provides a categorical resolution for this algebraic variety. So you know, from the classical point of view, it's even hard to say what can one mean by such a resolution, but still from a categorical point of view, you can do this. And I mean, this theorem turned out to be useful even for classical questions of algebraic geometry, like describing types like categorical properties of d of x for singular varieties. Okay, so how much time do I have? Close to 0, probably? Still 10 minutes, very good. Okay, so this is one example why categorical resolutions are useful. Because, as I said, you can think of them as better replacements for usual resolutions of singularities. So maybe let me give you a slightly less abstract example, another one. No, I mean, Hironaka works with algebraic varieties, which means reduced and irreducible varieties. And this one is not reduced, right? So that's the point. In this situation, you can't even say what is a Hironaka resolution. It does not exist because it works in a different situation. But from a categorical point of view, it exists. And it is quite simple and nice. So let me give you another example of a similar sort. So let us start with a nodal cubic, a plain nodal cubic. In P2. Then you can take a categorical resolution again in the form of derived category of a quiver. This time you need to take 3 vertices, 2 arrows here, 2 arrows here. So alpha 1, alpha 2, beta 1, beta 2, and impose two relations. Beta 1, alpha 1 is 0, and beta 2, alpha 2 is 0. So again, a very simple quiver, and you take the derived category of representations of this quiver, and this category turns out to resolve singularities in a categorical way for this curve, which is a non-normal curve. And like you can see, I mean, in this example, you can see the relation between this categorical resolution and the classical thing that you can apply here. So here you can, of course, apply the normalization procedure, which will give you P1, right? And there will be, and from the categorical point of view, you should also remember the point that was singular here. And you should remember that this point was obtained by gluing 2 different points of this P1. And so this part of the quiver corresponds to P1. So this is just the usual Kronecker quiver that corresponds to P1. This point corresponds to that point, and 2 arrows here correspond to the fact that you glue 2 points on P1, and the relation corresponds like to the fact that one of the points is 0 and the other is infinity. So there is something very similar that you can do in a much more general situation. Okay, so in a sense, so as I said, this part of the quiver corresponds to the usual P1, in the sense that one vertex corresponds to the sheaf O and the other corresponds to the sheaf O1. And the 2 arrows correspond to 2 maps between these sheaves. And there is one section, one map that vanishes at that point, and another that vanishes at that point. And these relations encode this. So you can think of beta 1 as of the fact that you glue this new point simultaneously to 2 different points of P1. So you should think that beta 1 is this part of the glue and beta 2 is this part of the glue. And one arrow here vanishes here and another arrow vanishes there at this point, right? And this translates into these 2 relations. Does it make sense? Okay, good. Mm-hmm. So, yeah, and actually the same happens for all other cases of this theorem. I mean, whenever you have a singular scheme, so first of all, you kind of, it may be non-reduced, then you use a certain procedure which is called the Auslander procedure to get rid of this non-reducedness assumption, and then it works in a way similar to this construction. Then you do something to get rid of reducibility or non-normality of your variety, which looks very similar to this procedure. And then you modify the Hironaka resolution of what you get in a result by adding some extra copies of derived categories of other varieties, actually mostly of the centers of your blow-up. So I don't have time to explain the details, but you can look it in the paper that we have. Okay, so yeah, so one moral of this is that you can improve the Hironaka resolution in such a way that first of all you include more schemes, so it becomes very general result. And second, you improve the categorical properties of your resolution, and it becomes really very well behaved. The pullback. No. In the Hironaka resolution, you may have several steps when you blow up some subvarieties. One feature is that you always blow up something smooth. And at each step, you have this partial resolution morphism. And you can ask whether this partial resolution morphism has this property or not. If it does, then you can just iterate and everything will be fine. But of course, at each step, it may this property may be not true. And then to cure this situation, you just need to consider the gluing of this partial resolution with the several copies of the center of the blow-up. You add some more information to your category, like replacing this small quiver with this bigger quiver. You kind of make your category bigger by adding some piece which is easy to control. It is just the derived category of the center of your blow-up, which is well understood triangulated category in a controllable way. And then you, at each step, you modify each step to make this condition to be true, and then you just iterate. So the procedure is inductive. It builds up on a Hironaka resolution, but it modifies it in a way to have this property, this crucial property. Okay, so that's one thing. And another thing is that, yeah, so as I tried to explain, these categorical resolutions that you obtain by modifying the Hironaka, the Hironaka resolution, they are usually much bigger because you have to add this information from the centers of your blow-ups, but they are better from the categorical point of view. Sometimes you can do the opposite. Sometimes it may happen that the Hironaka resolution by itself is good enough. It is a categorical resolution. But from a categorical point of view, you can replace the derived category of X tilde by some smaller subcategory, which still gives you a categorical resolution. And this is also very useful because, you know, in algebraic geometry, so the Hironaka procedure gives you just one resolution, which may not be the best one. I mean, there is an algorithm that you can pursue to obtain a resolution, but for some purposes you may need some better resolution. For instance, in the three-dimensional geometry, it is very nice when you have a small resolution of singularities, right? And the Hironaka procedure never gives you a small resolution. So sometimes you can find categorical resolutions that behave like small resolutions of singularities in the geometric setting when you don't have an actual small resolution of singularities. So let me say it again as an example, because I guess I don't have much time to explain. So for instance, if you have just a variety with an ordinary double point, in some sense, this is the most common type of singularity, right? Is an ordinary double point. Something that locally looks like the cone of a smooth quadric, right? Then it has a categorical resolution that behaves like a small resolution of singularities. So let me emphasize that this holds in any dimension, of any dimension. So, for instance, I mean, in the geometric situation, this is only possible in dimension 3, or maybe in some sense in dimension 2 also. So, geometrically, so if you have an ordinary double point in dimension 3, this means this is a cone over a smooth two-dimensional quadric, and the smooth two-dimensional quadric is just P1 times P1, right? So you have a cone over P1 times P1. If you blow it up, if you apply the usual resolution of singularities, if you blow up the vertex of the cone, then you will get smooth variety where the exceptional divisor of the blow up will be this P1 times P1. And sometimes in the geometric situation, you can contract this exceptional divisor in one of the directions. So sometimes, not always, you can replace this P1 times P1 by a single P1, and the usual resolution morphism, the blow-up, will factor into the composition of these two maps. So this is a small resolution, and this is the blow-up of this P1 inside this smooth variety. And working with this variety, I mean, replacing this resolution by this one is very useful. For instance, this is what makes possible one thing which is called a simultaneous resolution of singularities. So this is behind the simultaneous resolution, which works only in dimension 2, and which is a famous result by Briskorn and Galina Turina. And because of this fact that you have a very similar categorical resolution in arbitrary dimension, actually in arbitrary odd dimension it looks like this three-dimensional situation, and in arbitrary even dimension it looks like a two-dimensional situation. Because of that, you can construct a similar categorical simultaneous resolution for varieties of any even dimension with ordinary double points. So that's it, right? Okay, I'm sorry, yeah, that's the end of time, so let me stop here. Thank you.
Thank you. Are there any questions, comments? Yeah, we have a lot of them. Okay.
If your theorem doesn't, whether your whether your theorem doesn't is effective, or is it in existence?
No, I mean, it's as effective as Hironaka's theorem. We say precisely how to modify the Hironaka's resolution to make it work. No, we use Hironaka. No. So we take a resolution provided by Hironaka, and then we replace the derived category of each partial resolution that appears by another category, and this we do in a very precise way. We just consider a particular gluing of its derived category with the several copies of the derived category of the center of the resolution at each step. Yeah. I mean, the question is whether the push forward of the structure sheaf, the derived push forward of the structure sheaf, is the structure sheaf of your variety at the bottom. More or less, yeah. Mm-hmm. I mean, that's computable. Yeah.
So I have one question. In a small dimension, there is something like a minimal categorical resolution?
Yeah, that's a very good question. Yeah, so that's another reason why categorical resolutions are interesting, because you know this example that I mentioned in dimension 3, right? When we have a resolution given by a blow-up and another resolution which is smaller than that. In this situation, you actually have two different resolutions which are smaller than that. And this is a classical example that shows that geometrically you cannot expect to have a minimal geometric resolution. But in this three-dimensional example, these two small geometrical resolutions, they have the same derived category. They are derived equivalent. So from that point of view, in this case, you have a minimal categorical resolution. But in general, I don't know how to prove something like that. This is what one would like to believe to be true, but I don't know how to prove or disprove this kind of thing. Yeah, that's indeed one other perspective why this is an interesting point of view. Thank you for asking. Mm-hmm. 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 So probably the answer is no, because you see, actually in this definition, there is even no assumption that, I mean, you see, in the Hironaka's theorem, what he proves is that there is a proper birational map, right? So you can ask where here we have the property of being birational. Actually, we don't. So for instance, there are situations when you have a proper morphism from a variety of bigger dimension to your variety. And from a categorical point of view, as soon as the pullback functor is fully faithful, and this happens also, it is as well as a birational resolution. So your variety becomes bigger, but still it plays the same role. It allows you to replace a singular scheme by something smooth. So from that point of view, I mean, yes, I mean, you even don't have a birationality, so you can't talk about exceptional divisors or something else. But maybe under some additional assumptions, maybe you can extract something like that. Maybe that's a good question. I never thought about this. So you want to extract all these numbers, right? Mm-hmm. Mm-hmm. Yeah. Yeah, that's definitely a little bit different, but I mean, at least in some sense, one part of these questions is the questions about discrepancies of these exceptional divisors, right? The multiplicities in which they enter into the canonical class formula. And for instance, in some sense, if you want a Hironaka resolution to be categorical, right? If you want this property to be true, this is close to asking that the singularities are terminal or maybe canonical. So the singularities must be not very bad. And this gives you some restriction about discrepancies, right? Terminal means discrepancies are positive. Canonical means discrepancies are non-negative. So So the very definition gives you some bounds on these numbers. Maybe you, yeah, that's a good question. Actually, in some sense, you can extract some properties of the canonical divisor from a categorical resolution. So maybe you can, in some sense, extract discrepancies. But of course, there are more intersection numbers than just this. Maybe it's a good thing to think about. Thanks for asking. Yeah. Mm-hmm.
Do you have some kind of like categoric
Yeah. Sure. You can, as I said, you can extract some properties of the canonical divisor from that point of view, and in particular, you can state some property of a categorical resolution that will be equivalent to crepancy in the usual situation. But a funny thing is that actually you can do it in at least two different ways. So there is a notion of a weakly crepant categorical resolution and strongly crepant categorical resolution, and they are not equivalent. So in the geometric situation, both are equivalent to the usual crepancy, but in a general, I mean, you can just find simple examples when they're not equivalent to one another. Yeah. So there are no notions, but not just one notion, but at least two notions.
The question is, if you take the function homology of this derived category,
Okay.
and
Homology or co-homology?
homology,
Co-homology.
I'm expected to recover the Frobenius manifold.
Recover what?
Recover the Frobenius manifold.
Ah. No, I don't know.
So you have two different. Suppose you have two different resolutions, right?
I don't know. No, I don't know. Yeah. So in some sense, the Frobenius structure, it's on the other side of mirror symmetry, right? It's more about symplectic story.
It also can be
Ah. On the B side. Okay. I don't know. Yeah.
So you said that this, whether it's categorical resolution or not, say if we look something in the geometric framework might be related to whether it's to discrepancy.
Mm-hmm.
Is it necessary or sufficient?
So one implication, yeah. If I remember correctly, terminal singularities are rational. So if you have a variety with terminal singularities, then the Hironaka resolution is a categorical resolution, but not the other way around.
Okay, well, let's thank the speaker again for this very beautiful talk. And before all we go home,